A rotating steel shaft is supported at the end. It is subjected to a point load at the center. So we have discussed this case in a theory when we are defining the fluctuating load. In that case, we have a shaft is subjected to central load as well as axial load. This time it is subjected to only point load. The maximum bending stress produced is equal to 100 megapascal, and if the yield ultimate and the corrected endurance strength of the shaft material is 300, 500 and 200 megapascal respectively, factor of safety you have to calculate. He says that the rotating shaft and is supported at the end and only load acting is the point load. So we have shown here a shaft and we have one central load acting is equal to F, and we have two reactions, one at support A and other at support B, and the shaft is continuously rotating. When the shaft is continuously rotating, the bending stress is produced. So at the instant shown here, we have a compression on the top fiber and the tension on the bottom fiber. So if you take here one point P and you allow the rotation of the shaft, so the nature of the stress will continuously change as the shaft will rotate, and therefore we have variable value of a bending stress. So if we plot here a diagram of a stress versus time, initially the stress will be 0, then the stress will become equal to the bending stress. It will attain a maximum value when it is in tension. At the same time the bottom will be in compression, so as it rotates you will get a compression stress. So this one is our stress cycle, and we have mean stress this time will be equal to 0, and the amplitude stress will be equal to same as our bending stress, and we have given the value of the bending stress equal to 100 megapascal. We have given here the yield stress equal to 300, ultimate equal to 500 and endurance strength equal to 200, and this value of sigma A is less than AC, which is equal to 200 megapascal. So this one is a case of completely reverse loading, and in case of completely reverse loading we have mean stress equal to 0, and the amplitude stress is same as the bending stress. So we can use your SN diagram. So this value is same as our material strength. Value corresponds to 10 to the power 6 cycle will be equal to the endurance strength. Y-axis represent amplitude stress and the number of cycle. So SC value is equal to 200, sigma amplitude is sigma bending is equal to 100, that will be lower value. So we'll plot here sigma A value. So sigma amplitude will be equal to 100, endurance strength equal to 200. So at this time we have a infinite life because sigma A is less than AC. In that case we have a infinite life. And when we have a infinite life, in that case we have factor of safety will be equal to, you have to compare with SC and sigma A. SC is a higher value, so we have endurance strength divided by amplitude stress. We have endurance strength equal to 200 divided by amplitude stress equal to 100. So we are getting here factor of safety exactly equal to 2. This time the sigma M is equal to 0. And it is a completely reverse loading, so you have to solve the problem by SN diagram. And if the value of sigma M is not equal to 0, only in that case you have to use the different theory of fatigue failure. We can use Soderberg, Goodman, Gerber or ASME elliptic. A ductile material having an endurance limit of 196 megapascal, yield point SYT is 294 Newton per mm square is stress under the variable load. The maximum and the minimum stresses, that is sigma max and sigma minimum, are 147 and 49. Fatigue stress concentration factor is given 1.32, that is to be applied only to the alternating stresses. The available factor of safety for this loading we have to calculate. Now check what data is given. We have given the value of endurance limit and we have given the value of SYT. If you are knowing the value of endurance limit and the SYT, the theory that you can use is the Soderberg theory. Because if you recall here, Soderberg theory, we have a straight line joining from endurance limit to SYT. We can use here ASME elliptic line also. Two theory we can use. One is Soderberg and one is ASME elliptic. According to ASME elliptic, we have 1 upon n square, that is a factor of safety square, is equal to mean stress divided by SYT whole square plus sigma amplitude by AC whole square. But as far as the gate exam is considered, you have to only select the Soderberg theory. So let's collect the data here. We have endurance strength is equal to 196 megapascal, SYT is 294, sigma max is 147 and sigma minimum is equal to 49. To solve this equation, we require the mean stress and the amplitude stress. And we know here that the mean stress is given as sigma max plus sigma minimum by 2, that will be equal to 147 plus we have 49 divided by 2. So in this case, you will get the mean stress equal to 98 megapascal and the maximum stress equal to 147, that is sigma max minus sigma minimum minus 49 divided by 2. So you will get a mean stress equal to 49 megapascal. The fatigue stress concentration factor is Kf is given as 1.32. So we'll solve this problem only for Soderberg. So the amplitude stress you have to multiply it by Kf. Remember here the fatigue stress is same as sigma maximum value will be same as the fatigue stress multiplied by sigma amplitude. So every time you have to multiply the sigma to generate the maximum value of alternating stress. So let's substitute here. We have 1 by n, mean stress is equal to 98, SYT is equal to 294 plus we have sigma A, that is the alternating stress equal to 49. Fatigue stress concentration factor is 1.32 divided by endurance strength, which is equal to 196. Solve this, you will get the value of n, that is a factor of safety. So you will get a factor of safety close to 1.5. A forged steel link with a uniform diameter of 30 mm at the center is subjected to an axial force that varies from 40 kN in compression to 160 kN in tension. The tensile yield and the corrected endurance strength of the steel material are 600, 420 and 240. So 600 you have to take as the ultimate value, 420 is yield and the endurance equal to 240. The factor of safety against the endurance limit as per the Soderberg criteria we have to find out. According to the Soderberg criteria, the factor of safety is given as 1 upon n equal to mean stress divided by SYT plus we have alternating stress divided by endurance strength. Mean stress and the alternating stress will calculate here first. So let's represent here a forged steel link of diameter d is equal to 30 mm. So we have d is equal to 30 mm. One time we are applying here a compressive force. So first time we apply a compressive force. So let's call this one is F minimum, because magnitude wise 40 is less as compared to 160 in tension, and this value will treat as a negative value is minus 40 kilonewton. Second time we subject it to a maximum force equal to tension, that will be taken as a positive value is 160 kilonewton. Now using the diameter, minimum force and maximum force, we can first calculate here what is the value of maximum stress and minimum stress. Then we can calculate sigma mean and sigma amplitude. We require the value of SYT. Out of 600, 420 and 240, SYT is equal to 420. So only data you have to collect that is required by the given equation. So we have SYT equal to 420 megapascal. We require the endurance strength SE, that equal to 240 megapascal, and sigma m and sigma a will calculate from this. So let's first calculate here what is the value of sigma maximum. Sigma maximum is same as F max divided by area, which one is circular section. So we have 4 times of F max divided by pi d square. So that will be equal to 4 maximum force is equal to 160 kilo is 10 to the power 3 divided by pi into d square is 30 square. So we'll get here the maximum stress close to 226.47. That will be megapascal. In the similar fashion, we can calculate the minimum stress. So that will be equal to 4 times of the minimum force divided by pi d square is same as equal to 4 times. Compression force will take it negative, so we have minus 40 divided by pi. We have diameter equal to 30 square. So this one is a compressive stress is negative 56.62. That will be megapascal. Then we'll keep our two calculation ready. One is the mean stress and one is amplitude stress. Mean stress is sigma max, which is equal to 226.47 plus we have minimum stress equal to minus 56.62 is divided by 2. So we have mean stress value come out to be 84.92. Again, it's a megapascal. And the amplitude stress is given as maximum minus minimum by 2. So that will be equal to 226.47 minus become plus is 56.62. Again divided by 2. Amplitude stress is equal to 141.52. The mean stress is not equal to 0, therefore we are using the Soderberg criteria. So we have 1 upon factor of safety n equal to mean stress is 84.92. 84.92 SYT is equal to 420 plus amplitude stress is equal to 141.52 and the endurance strength is equal to 240. So factor of safety according to the Soderberg criteria come out to be 1.26. So in some numerical you have to do the extra calculation of maximum and minimum stress. Rest procedure is remains same. A bar is subjected to fluctuating tensile load from 20 kilonewton to 100 kilonewton. So both time it's a tensile. Previous problem we have tensile and compressive. So here the maximum and the minimum stress will be tensile only. The material has a yield strength SYT equal to 240. Endurance strength limit in bending is 160. According to the Soderberg principle, the area of the cross section in mm square of the bar for a factor of safety equal to 2 you have to find out. Now this one is a slightly reverse problem. We have to find out here the area. So according to the Soderberg criteria, we have 1 upon n is equal to mean stress divided by SYT plus amplitude stress divided by endurance strength. Already he has given the value of SYT, that is the yield stress, is equal to 240 megapascal, and the endurance strength is also known, that equal to 160. So your job is to calculate the value of mean stress and the amplitude stress in the form of unknown, that is equal to area, and we have to use the factor of safety n is equal to 2. So let's say that this bar has a cross section area equal to A. We don't know what type of cross section is, and is subjected to initially a tensile load of minimum force. So out of 20 and 100, 20 is minimum and is positive value. Second time we apply the maximum force F max equal to 100 kilonewton. We can calculate here the minimum stress and maximum stress. So we have sigma max will be equal to force upon area. So this time we have to use the maximum force. We have maximum force equal to 100 into 10 to the power 3 divided by area A, and we have minimum stress corresponds to minimum force, that is F minimum divided by area. So we'll get here the minimum stress produced will be equal to 20 into 10 to the power 3 divided by the same cross section area equal to A. Now we know the value of max and the minimum, so we can calculate here the maximum stress. Area will take it common, So this value will be same as equal to 1 upon A into 100 into 10 to the power 3 plus 20 into 10 to the power 3, and whole thing is divided by 2. 120 is 120, so we'll get this answer equal to 60 into 10 to the power 3 divided by area A. Same thing will repeat here also. In that case, 1 by A we can take it common. What we left is 100 minus 20 divided by 2, and 10 to the power 3 will again take common. We have 100 minus 20 equal to 80. 80 divided by 2 is 40. So we have 40 into 10 to the power 3 divided by area A. Let's substitute here. We have 1 upon factor of safety equal to 2. Mean stress is given in the form of 1 by A. So 1 by A is taken common from both the terms here. Mean stress equal to 60 into 10 to the power 3. Area already taken common. We have SYT is equal to 240 plus amplitude stress is 40 into 10 to the power 3. Even we can take out here 10 to the power 3 also common. Let it be. We have endurance strength equal to 160. So only unknown in this equation is A. Solve it. You will get the area close to 1000 will be mm square. A machine component made of a ductile material is subjected to variable loading with an minimum value is equal to minus 50 and the maximum value equal to 50. The corrected endurance limit and the yield strength of the material are 100 megapascal and 300 megapascal. The factor of safety we have to find out. So we'll check here first the type of loading, and then we can think of the theory for Soderberg because he has given the value of SY. So in this case we have sigma minimum is given as equal to minus 50 megapascal and sigma maximum is given as equal to positive 50. Clearly this one is a alternating stress. The mean stress will be equal to sigma maximum plus sigma minimum by 2 is positive 50 minus negative 50 divided by 2, that equal to 0. And sigma amplitude will be equal to sigma max, which is equal to 50 minus minus is plus, again we have 50 divided by 2. So we have amplitude stress equal to 50. So this one is representing the completely reverse stress. And in addition to this, we have given the endurance limit. Only data required is the endurance limit because we are going to solve the problem by SN diagram. So we have endurance limit is SE is equal to 100. And this value of SE, which one is 100 megapascal, is greater than the value of sigma A, which is equal to 50. It means that we have a infinite life. So we'll use the SN diagram here to find out the factor of safety. Endurance limit is equal to 100 megapascal and the amplitude stress equal to 50. Since here 50 is less than 100, we have infinite life. In this case, we have factor of safety N is given as endurance strength SE divided by amplitude stress sigma A, which is same as equal to 100 divided by 50. So we have factor of safety is equal to 2. Even the Soderberg criteria will solve this problem because this axis is included in our fatigue theory. So we have 1 upon N. Mean stress value is equal to 0 divided by SYT. And now this time I have to collect the data for SYT. We have SYT is equal to 300, but this term is 0 plus amplitude stress is equal to 50. That will be divided by endurance, which is equal to 100. So this and this will be the same equation. So we are again getting the value of N is equal to 2. Both method will work this time. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.